Fuel system. General electronic engine controls have allowed great increases in controlling the metered fuel flow to the engine. Engine fuel systems have become very accurate at providing the correct mixture of fuel and air to the engines. Gas turbine fuel controls have also greatly improved the ability to meter the fuel correctly during all flight regimes. Improvements in electronics and the use of digital computers have enabled the aircraft and engines to be electronically interfaced together. By the use of electronic sensors and computer logic built into electronic controls, the engines can be controlled with much more accuracy. Fuel cost and availability have also become factors in providing engines with fuel systems that are efficient and very precise in scheduling fuel flow to the engine. Many engines use an interactive system that senses engine parameters and feeds the information to the onboard computer. Electronic engine control. The computer determines the amount of fuel needed and then sends a signal to the metering device. This signal sent to the metering device determines the correct amount of fuel needed by the engine. Electronic controls have become quite common with gas turbines and have increased the capabilities of the fuel system, making it less complicated for the technician and decreasing maintenance problems. Engine fuel systems can be fairly complicated, yet some are quite simple, such as on small aircraft with a simple gravity feed fuel system. This system, consisting of a tank to supply fuel to the engine, is often installed in the overhead wing and feeds a small float-type carburetor. On multi-engine aircraft, complex systems are necessary so that fuel can be pumped from any combination of tanks to any combination of engines through a cross-feed system. Provisions for transferring fuel from one tank to another may also be included on large aircraft. Vapor lock. All fuel systems should be designed so that vapor lock cannot take place. Older gravity feed systems were more prone to vapor lock. The fuel system should be free of tendency to vapor lock, which can result from changes in ground and in-flight climatic conditions. Normally, the fuel remains in a liquid state until it is discharged into the airstream and then instantly changes to a vapor. Under certain conditions, the fuel may vaporize in the lines, pumps, or other units. The vapor pockets formed by this premature vaporization restrict the fuel flow through units which are designed to handle liquids rather than gases. The resulting partial or complete interruption of the fuel flow is called vapor lock. The three general causes of vapor lock are the lowering of the pressure on the fuel, high fuel temperatures, and excessive fuel turbulence. At high altitudes, the pressure on the fuel in the tank is low. This lowers the boiling point of the fuel and causes vapor bubbles to form. This vapor trapped in the fuel may cause vapor lock in the fuel system. Transfer of heat from the engine tends to cause boiling of the fuel in the lines and the pump. This tendency is increased if the fuel in the tank is warm. High fuel temperatures often combine with low pressure to increase vapor formation. This is most apt to occur during a rapid climb on a hot day. As the aircraft climbs, the outside temperature drops, but the fuel does not lose temperature rapidly. If the fuel is warm enough at takeoff, it retains enough heat to boil easily at high altitude. The chief causes of fuel turbulence are sloshing of the fuel in the tanks, the mechanical action of the engine-driven pump, and sharp bends or rises in the fuel lines. Sloshing in the tank tends to mix air with the fuel. As this mixture passes through the lines, the trapped air separates from the fuel and forms vapor pockets at any point where there are abrupt changes in direction or steep rises. Turbulence in the fuel pump often combines with the low pressure at the pump inlet to form a vapor lock at this point. Vapor lock can become serious enough to block the fuel flow completely and stop the engine. Even small amounts of vapor in the inlet line restrict the flow to the engine-driven pump and reduce its output pressure. To reduce the possibility of vapor lock, fuel lines are kept away from sources of heat. Also, sharp bends and steep rises are avoided. In addition, the volatility of the fuel is controlled in manufacture so that it does not vaporize too readily. The major improvement in reducing vapor lock, however, is the incorporation of booster pumps in the fuel system. These booster pumps, which are used widely in most modern aircraft, keep the fuel in the lines to the engine-driven pump under pressure. The pressure on the fuel reduces vapor formation and aids in moving a vapor pocket along. The boost pump also releases vapor from the fuel as it passes through the pump. The vapor moves upward through the fuel in the tank and out the tank vents. To prevent the small amount of vapor that remains in the fuel from upsetting its metering action, vapor eliminators are installed in some fuel systems ahead of the metering device or are built into this unit. Basic fuel system. The basic parts of a fuel system include tanks, boost pumps, lines, selector valves, strainers, engine-driven pumps, and pressure gauges. A review of fuel systems in the Aviation Maintenance Technician General Handbook provides some information concerning these components. Generally, there are several tanks, even in a simple system, to store the required amount of fuel. The location of these tanks depends on both the fuel system design and the structural design of the aircraft. From each tank, a line leads to the selector valve. This valve is set from the cockpit to select the tank from which fuel is to be delivered to the engine. The boost pump forces fuel through the selector valve to the main line strainer. This filtering unit, located in the lowest part of the system, removes water and dirt from the fuel. During starting, the boost pump forces fuel through a bypass in the engine-driven pump to the metering device. Once the engine-driven pump is rotating at sufficient speed, it takes over and delivers fuel to the metering device at the specified pressure. The airframe fuel system begins with the fuel tank and ends at the engine fuel system. The engine fuel system usually includes the engine-driven pumps and the fuel metering systems. In aircraft powered with a reciprocating engine, the engine-driven fuel pump and metering system consists of the main components from the point at which the fuel enters the first control unit until the fuel is injected into the intake pipe or cylinder. For example, the engine fuel system of a typical engine has an engine-driven fuel pump, the fuel air control unit, metering device, the fuel manifold valve, and the fuel discharge nozzles. The fuel metering system on current reciprocating engines meters the fuel at a predetermined ratio to airflow. The airflow to the engine is controlled by the carburetor or fuel air control unit. The fuel metering system of the typical gas turbine engine consists of an engine-driven pump, fuel flow transmitter, fuel control with an electronic engine control, a distribution system or manifold, flow divider, and fuel discharge nozzles. On some turboprop engines, a fuel heater and a start control is a part of the engine fuel system. The rate of fuel delivery can be a function of air mass flow, compressor inlet temperature, compressor discharge pressure, compressor revolutions per minute, RPM, exhaust gas temperature, and combustion chamber pressure.